Hello, everybody, and welcome to the Data Science Milan meetup of October. Today, we're gonna talk about optimizing differential equations using reinforcement learning and genetic algorithms. Let me give you a brief introduction of our community. We are an independent group that was founded on February 2016. Nowadays, it counts more than 1.7 thousand members, and we typically meet once a month. We are part of a greater association called the Italian Association for Machine Learning. And this is the staff. Those are the people who are behind the organization of the events, like tonight. If you are interested and would like to be part of this staff, organizers, and keep in touch with us, in particular, we're looking for a social media manager at the moment. This is our website, www.datasciencemilan.org. And if you go on the website, you're going to find the recordings, the slides of all of the previous talks. There is also a link to our blog on Medium, where you can find the summaries of past events. And you can also find a section for joining the newsletter. We send one email per month, and we typically group together relevant news, articles, shared from the community, and things related to data science and artificial intelligence, in particular also events happening in Europe or online. So please join and support our newsletter. We also use Slack as a main communication channel. Again, on the website, if you scroll to the bottom of the website, you can find a link for receiving an invite. Okay, so if you wanna give a talk to one of the next meetup, this is our email, datasciencemilan@gmail.com. Send your proposal. And for today, we have Alberto Prospero, lead data scientist at Eni, and Salvatore Guastella, data scientist at Eni. Before we start with the tech talks, need to ask you a favor. Those are our handle, our accounts on the main social media platforms. Please help us spreading the word. Tweet about us, create some posts, share our
dancing on dangerous.
Momento. Adesso sì, si dovrebbe sentire, sì, c'è una musica di sottofondo.
Ok, possiamo andare avanti? Okay, so let me share the screen so we can start the presentation. Okay, can you see the screen?
Yes.
Okay, great. So I will give you just an overview of the presentation, and the presentation is divided in 4 parts. The first one, in the first one, we will see the aim of R&D, so research and development, and the connection with data science. We will talk then a little bit about data science as a tool to accelerate the development of new technologies. We will go to the core of the presentation, meaning the Varde pool oscillator, when we will see basically both reinforcement learning and genetic algorithm applied to this toy example. And finally, we will have just a brief grasp about the real project where we applied the kind of technologies and models that we are going to introduce you in a minute. So before starting, I'd like just to introduce you the data science team. Here we represented all the team in a big picture. We are quite a big team. We are 15 data scientists and work in the digital department and serve diverse businesses and stakeholders. And for example, one of the main areas that we are working in is in the scope of the presentation, because it's research and development, where we try basically to boost in and help in the research of new renewable energies. Also, we work in the production, trying to improving the production in oil and gas plants. And another big project, I'd say, is related to drilling, where basically we try to identify best sites to drill and, in general, optimizing drilling processes. So, going to the first part of the presentation, I'd like just to introduce to you why data science applied to research and development. So, as I was mentioning you before, R&D, so research and development, tries to find new technologies to contribute to a sustainable energy transition for green energy production. And the main phases when we talk about research and development are those that are reported in the slide. Because we have an initial phase, which is the design phase, where basically we're trying to define and identify a possible solution, a possible new technology. Then what is done is the creation of a prototype in a controlled environment, for example, in a laboratory, where we can test and see if the solution that we are developing is working in a controlled setting. And finally, the final phase is the scale up of the solution, right? We basically industrialize the prototype and try to see if in the real environment, in the real scenario, brings value and brings money to the company. And it is important to notice that in all the reasoning, the amount of time that it is spent, generally speaking, is about years. It is not about months, but design, validation, and industrialization lasts for years in general. So how data science can help in this sense? Well, if you assume for a minute that we managed to create a simulator environment where we can apply models and apply data science techniques, you can realize that data science allows both to accelerate the experimental validation process and also lowering the risks. Because if we have data science techniques applied to the simulator, maybe we can more quickly understand if the solution that we are going to prototype is going to bring some value or not. Because basically in the simulation environment, each simulation might take 30 seconds, 1 minute, 5 minutes, 10 minutes, and not days as in the real case. And also we can test a more a broad set of parameters and variables. And so we can also spot some critical scenario that otherwise would have been difficult to identify, right? And so we can also lower in the risks. So I leave the floor to Salvo to introduce you a little bit more in details what are the models that we can apply in research and development.
Okay, as you can see from the slide, the focus of this presentation will be optimization. Well, what are the goals of optimization? Pushing technologies to their boundaries and, as Alberto said, accelerate the experimental process. How to do that? Developing prescriptive algorithms that identify what actions to take and developing high-level control of the system. In our R&D project, we also work on, let me say, classical machine learning models, for example, predictive model, anomaly detection, and so on, but also on process simulation that could be data-driven or not, and model calibration. But what does optimization mean, at least for us in our context? It means studying and understanding how a new technology works. It means how to measure its performance and to control and optimize the whole system. In today's presentation, we will focus on the question, how can I select the best controls or the best actions in order to optimize the performances of the process? In order to show you the methodology and techniques that we used in one of our projects, we'll use a toy example, which is the Van der Poel oscillator problem. It is a dynamic optimization problem, so time must be taken into account. The goal is to find the control function u of t inside a range of -3 and 1, as you can see from the first constraint, that minimizes the objective function f of u in an environment that is defined by a system of three differential equations on x1, x2, and x3. As you can see from the second constraint, the value of x1, x2, and x3 at time 0 is fixed, as well as the final time, tf, which is 5. So how did we approach that problem? We use two different algorithms. The first is the differential evolution algorithm, which is part of the genetic or evolutionary class. And the second one is the reinforcement learning, the less known and explored of the three basic machine learning classes. Of course, the other two are the supervised and unsupervised learnings. Those are the four main steps of the differential evolution algorithm. So first, a population of individuals is defined. But what is an individual? It is simply a vector or a possible configuration of the control variables. At the first iteration, it is randomly generated. The second step is the evaluation step. Evaluation of what? Of the objective function of each individual. The problem is solved using each individual's vector as input. And in this phase, is the best solution so far is identified. Then for each candidate, a mutant candidate is generated using a linear transformation of other randomly selected candidates. We'll focus on that in a minute. And lastly, the recombination phase. Vectors are recombined using elements from the best and from the mutant candidates. If a recombined candidate has a lower objective function, the original population candidate will be replaced. Otherwise, the population candidate will be part of the new population and the process starts again. So this is the optimization process for the Van der Poel problem. In the whole slide, you can see the subscript index I, which refers to discretization of the time in any intervals of delta t width. Of course, it can be smaller or larger depending on the problem you are working on. So in the first step, we define a population of candidates, which are A, B, and so on until Z. Each candidate is a vector of u's, u0, u1 until un, which is the number of interval. For each candidate, the objective function is evaluated using the definition of the environment. In this way, the best solution vector, which is indicated with u star, is identified. After that, if the stop criteria is not met, and I'll explain it in a moment, the algorithm goes through the mutation and recombination phases, defining a new population, and a new iteration starts. The stop criteria is met if the number of iterations reaches the maximum, or the standard deviation of the objective functions of candidates, which is indicated with J, is less than a defined threshold epsilon. That means that new candidates do not improve the objective function and a minimum is reached. Here is a focus on the mutation and recombination phases. There are several differential evolution strategies, but here we uh, describe the best one being strategy. The mutant vectors are obtained adding to the best vector the difference, from here the name differential evolution, between two randomly selected candidates from the population RAN1 and population RAN2, multiplied by m, which is a constant, the so-called mutation constant. The recombined vector is obtained in this way. For each element of for each one of the n elements of the vector, a random value between 0 and 1 is generated. For example, we take the first row with the O element. We have a rand 0, which is the random value between 0 and 1. If that value is less than epsilon, which is called the crossover probability, the element is replaced with the element from the mutant vector. Otherwise, in the case of rand1 in the line 1, which is greater than or equal to the crossover probability, the original best value is selected. So we repeat this process for the n value of the vector. So we have a new candidate solution, the recombined vector, that will be evaluated and may be part of the subsequent population. Here you can see the Python implementation of the van der Poel problem. First, we have the definition of the environment, which is a function of the array x, of time, and of the u function, which in turn depends on time. Then we have the objective function that depends on u and has the odint function inside, the odint function from scipy.integrate, which is used to solve the system of ordinary differential equation. And finally, we have the constraint definition and optimization using SciPy's differential evolution. As you can see from the parameters workers, it has a native multiprocessing support that can speed up a lot the algorithm. In these plots, you can see the result of the optimization process. On the left, you can see the control function u, while on the right, we have the state variables x1, x2, and x3. As you can see, the solution is similar to the benchmark solution, which is shown in the smaller picture. It is less smooth and there's some noise, but it is qualitatively similar. So that's all for the first algorithm that we used to solve the van der Poel problem. Now Alberto will show you the second approach with the reinforcement learning.
Thank you, Salvo. So we are going to discuss the second approach related to reinforcement learning. To start, just some history about the reinforcement learning. Reinforcement learning was dated is dated around 1950, when Richard Bellman and other colleagues basically formalized the problem and defined some critical values and critical elements of reinforcement learning, like Bellman equation, like dynamic programming, like Markov decision processes. Some of you might ask, what is the difference among reinforcement learning and optimal control theory? Well, the answer, according to Quora, is that optimal control theory works, and this is partially true. Because optimal control theory and algorithms related, like model predictive control, for example, are for sure more stable and studied from a mathematical point of view. But indeed, reinforcement learning, especially during the last years, achieved some quite important milestones. And so, especially in games, reinforcement learning is every day more utilized. So before starting to share what is the exact algorithm that we applied to solve the basically control problem, I'd like to give you some fundamentals about reinforcement learning. So reinforcement learning is based on agents that act within an environment. And the environment represents basically an external world that the agents want to control and want to interact to. So at every step, basically, the agent produces an action, the action is provided to the environment, and the environments basically return two quantities. The first one is the reward, which is a numerical score of how good was for the agent in that particular state, in that particular situation, to take that particular action, and it is indicated with the RT plus 1, and also returns a new state, so a new configuration where the agent indeed can act. And it is important to notice that the states, generally speaking, are stochastic, meaning that in some certain situation we might end up in a new state, and in other situations, instead, even if the action is the same, we might end up into another state. And also, it is important to notice that, generally speaking, there are two kinds of, I'd say, learning tasks, but let's say environments. One is the so-called episodic task, meaning that we have an ending state. So at a certain point, the interactions among the agent and the environment stops and stop into an ending state. While there is another option that is no-stop actions, and so the agents keep interacting indefinitely with the environment. And this kind of task, this kind of environment is called continuing environment. So in our case, the environment is, as you can imagine, the different set, the differential equations. And before going into the next slide, I'd like to provide you with two important definitions. One is the policy, and the other is value function. So what is the policy? The policy represents basically a sequence of actions. So it is a function that maps from each state what is the probability for the agent to take that particular action. And so it is indicated as pi of u given x. Given that I am at state x, I tell you what is the probability for the agent to take action u. Value functions instead are a quite important concept in reinforcement learning because they allow us to have a clear score of how good is for the agent to be in a given state. And we will talk about state value functions, or it is also the measure of how good is for the agent to be in a given state and to take a particular action. And in this case, we will talk about action state value functions. So this is just a brief overview of reinforcement learning. In the next slide, I'm going to introduce you what is the aim of reinforcement learning. And the aim of reinforcement learning, as it is reporting to the slide, is just to maximize what is called the total expected return. So if we define the return as the sum of the rewards that the agent receives across all the action that it takes with the interaction with environments, we can define the return as the sum of these rewards discounted by the quantity, which is gamma, that generally speaking goes from 0 and to 1, and serves for the agent to basically tell the agent that more future rewards are less important with respect to the closer ones. And so we are ready to define the actual problem of reinforcement learning, which is to find basically the policy pi, so the sequence of actions pi that maximizes the total expected return. So if we define g of 0 as the initial return, the total expected returns basically is the average of all the returns that we can receive, that we can gain across all the possible states that we can encounter with interaction with the environment, and with respect to all the probabilities that our policy prescribes to take. And so it is basically a quite big average of the returns that we get across the policy that we are using and the dynamics of the stochastic environment that we might have. Okay, and about the episodic environment, how is the process? As I was mentioning before, we are in initial state, which is called x0. We take an action u0. The environment responds with a new state, x1, and a new environment, r1, and this is called a step. And then the process repeats, right? So we have a new action, a new reward, and a new state, and so on. How can we learn the best policy? The typical process basically is to use experience in order to solve the reinforcement learning problem. And to do that, basically, we generally speaking have three approaches. The first one is to try to approximate the best policy pi directly. So we set up algorithm to try to find the best policy in a direct way. And for example, the algorithm policy gradient tries exactly to do that. But one other big basically one other big set of algorithms is prescribes to find the best basically the best action or state value functions, and starting from that try to identify the best policy. So we find the value functions and the optimal value function, and with that basically we approximate the policy pi. And finally, the third approach instead is to use a mix of both of them. So we try in a simultaneous way both to approximate the best policy and both to find the best state value function or action state value function. And just to give you some equations about the state action value function, and basically also introducing you the Bellman equations, we can say that the state action value function, indeed, it is the average of the return that is taken starting from a state xt and taking action udt. And depends on policy pi, because depending of the sequence action that we take, we can have different values of this quantity q, that it is the action state value function. And the important thing about the work of Bellman are indeed the two last equations with respect to the action state value function. We also have two similar equations for the state value function. And Bellman says that the value of this q, so the value of the state action value function, indeed can be expressed in a recursive way, right? Because we can express the value of this function at time t in terms of the value of the function at time t plus 1. And also there is an optimal Bellman equation that it is written for the optimal policy. So for the optimal policy, this is the equation that must hold. And so Q star at time t is expressed as the previous equation with Q star at time t plus 1. Okay, so what about the algorithm that we implemented? The algorithm that we implemented uses both an approximation of the policy, pi, which aims to find basically the best action to take in a given state, but also tries to approximate the optimal value of the state action value function, and does this by using two neural networks with respectively have weight rho and w. Also, this kind of algorithm is a deterministic algorithm. So the policy that is returned is a deterministic policy. And this is because, as I was mentioning you before, we are trying to approximate the optimal policy, right? And also, it works just in a continuous action space and uses a replay buffer. What is a replay buffer? Well, basically, it is just a storage where we can store values and that has some capacity, and we sample a training time from this replay buffer, usually in a random way. So before you to going a little deeper into how these algorithms work, I like you to provide you the general idea which is behind. And to do that, I need to go to the previous slide and in particular focus on the last equation. Because from this last equation, what we can do and what is usually done, for example, in Monte Carlo or 2D learning, is to sample this average by using Monte Carlo, and basically, instead of computing the exact value of the expectation, which would be quite complicated, we sample starting from state X up to the end state, the quantities that are reported into the square brackets. And so we sample RT plus 1 plus gamma max of Q star across all the actions. And if we have a neural network, basically, we can try to approximate this sample that when averaged, give you the exact value of the expectation and construct also a loss. So the loss will try to minimize the error among the predictions that we have from our neural network and the samples that we retrieve from planning the episodes into the environment. The important thing to notice is that since we are in a continuous setting, this max cannot easily calculated, but needs quite a dedicated subroutine. And so in order to approximate this max, what we do actually is to use pi, is to use exactly the policy pi, which we are trying to maximize, that returns the best action that we can take in a given state. Okay, so this is the main reasoning that stays behind. And now we are ready to describe what is the pipeline of the algorithm, as we can see. So the first phase is just to sample, is to play within the environment. And so we are at state xt and use policy pi to interact with the environment and to store the values into the replay buffer. You can see that here there is a noise that is added, and this is done because we want to be sure to continue to explore the environment, right? And so we add some noise in order to do that. The policy pi in time will be deterministic and will find the max, and so will not explore by itself. And so this noise is added for this reason. Then what we do is actually the learning, and the learning basically is as follows. So we try to construct this q tilde, which is exactly what I showed you before in the last equation between the square brackets. So we have rt plus 1 pu gamma times q next, and q next is the maximum, but the maximum is not computed directly, but is computed by using this policy pi. And when we have q tilde at this time, as I was mentioning you before, we can compute the loss function and train exactly the neural network. One last step instead is done to define and train the policy pi. And to train the policy pi, we can directly use the function q, the state action value function, because it's continuous and differentiable with respect to pi. And so we can compute the gradient and solve with respect to policy pi and optimize also this policy. There are also other details that are not mentioning here, but I leave you the article if you want to deep dive more in details. But now I'd like to show you in concrete, basically, the code that we implemented. So we use the TensorFlow library, which, as you can imagine, is based on TensorFlow. And in this snippet of code, we basically define the agent that needs a policy and an actor and a critic that are two neural networks that we define in here. And then we define here state and actions that are just two vectors. So how can we define basically the environment as it is proposed into the slide? So the van der Poel equations are the same as Salvo introduced you before. Here in the step, instead, what we did is to solve for a little bit of time, so up to t plus delta t, the differential equations, which returns the exact value of x1, x2, and x3 from t up to t plus delta t. And then we can compute the reward, compute the next state, and return the next state and the reward. It is important to understand how we computed the reward. So to compute the reward, basically, we had two choices. The first one was not to provide any reward through each timestamp that we basically perform and provide all the rewards at the very ending. But this kind of approach would have slowed down the learning, because in gradient ascent, basically, we have a lot of rewards that are zero and one single reward at the end of the episode that has value different from zero. And the second approach instead, which is what implemented, prescribed to provide a step reward that is given by minus the difference of x3. So it is minus the increment of x3. And it is important to notice that when we sum up at the end of episode, we exactly obtain minus x3 of TF. So if you imagine for a second to not consider this minus, at the end of episode, we are trying to maximize x3 of TF, but the original problem prescribed not to maximize, but to minimize, and this is the reason for this minus. Okay, so here we introduce in the left snippet of code basically just the typical cycle of reinforcement learning, where we have the define the state, we act, we receive a state, a reward, and if it is a terminal state or not. And then within this observe, there is basically the learning of the algorithm. And as you can see, the interesting part is that actually in time, the average episode reward increase. So actually our algorithm is learning. And this slide instead is to provide you with the exact results that we obtain after training. And on the left plot, basically, you can see that we manage to approximate the exact control function u by using reinforcement learning. And also, if we compare these results with genetic algorithm, you can observe that it is more smooth. And so this is a good hint that tells us that this algorithm probably generalizes better, at least in this scenario. While on the right, you can see that the evolution of x1, x2, and x3 is more or less the same as the original solution. So in this slide, it said we are going to discuss a little bit about the benefits of reinforcement learning and genetic algorithm. So reinforcement learning is for sure much more flexible in terms of the choice of delta t and number of control variables, while genetic algorithm, especially if we reduce delta t, this could cause a large increase in terms of computational time. From point of view of convergence, instead, it is easier to let genetic algorithm converge to a good solution, while instead reinforcement learning is not so easy, especially when we use neural networks, because we have a lot of parameters such as learning rate, number of hidden layers, and so on. While in terms of generalization, at least for this problem, it seems that reinforcement learning generalizes better, right? Because we had quite a smoother solution that led us to hope for the good. Okay, so this is all for the toy example. I have just a final slide to tell you where we applied these kind of models. And the project is called microalgae, and basically it is a work to try to fix carbon dioxide through the cultivation of microalgae, and basically is collocated in the process to reduce the emission of climate change gases and to use renewable energies and sustainable energies. If you want more details, you can go on this video on YouTube. So we stop here. Thank you for the attention. And if you have any questions, we are more than happy to answer.
Thank you, Alberto, and thank you, Salvatore. Let me read the YouTube chat to see if there are any questions at the moment. Okay. I don't see anything in the chat, so please let's give a few minutes because there is always some delay. So if anybody want to ask something to Alberto or Salvatore, please add your question into the chat. Otherwise, they will be sharing with us the slides, and you can also find this recording on YouTube. Will be available to watch offline. And in the summary article, we will put all the references, links. So if you want to learn more about, you will be able to contact directly Alberto Salvatore. Okay. Thank you very much. That was very advanced use case of artificial intelligence. So congratulations.
Thank you.
And yeah, we were really glad to have you as a presenter to the meetup. And I hope to see you again.
Yeah, thank you, and thank you, everybody.
Thank you, Gianmario. Bye.
Bye.
Fabio è staccato?